So we were talking about looking at residuals. And I said one of the things we do is we look at the standard deviation for the residual idea, which is called the standard error in our ANOVA calculations. So when I do our study time example, we see up there in the regression statistics, that summary output at the top, a standard error. I could do the actual then residual for each value. I have to do that directly from the data. So let's go back and do that in our data analysis. Regression. Y range is exam score. X range is the study hours. Oop, I need all of the study hours, please. Thank you. Yes, there are labels. I'll make it a new. I'm going to tick all of these boxes this time. So it's going to generate a bunch of stuff for me. But the first two are residuals and standardized residuals. So over here in the left, there's my standard error. And here down at the bottom, I have the predicted exam score. That would be what we get if we put our X values into our regression equation. I get the residual, which is the difference between the actual number and the predicted number. And then I divide that by this standard error here to get these standardized residuals. And again, none of these are particularly out of line. I don't see anything below -2 or above 2. And I can say, well, that's pretty good. I can think that these should tell me this data is close enough not to be unusually bad on my residuals, because that would violate the idea that our residuals, our error, was not normally distributed. But another way to do this is what's called a normal probability plot, or a quartile plot. Hey, wait a minute, I know those words. So I could think of this, instead of doing just quartiles, I could do any sort of quantile here. Let me make this particular chart bigger. This plots the residuals in ranked order from lowest residual to highest residual against a normally distributed idea. So my assumption is that I should get a normal distribution. Using our normal inverse calculator, I can say, okay, well, if it was normally distributed, my residual should look like what? If that's not a roughly straight line, then I have a problem. How's this one? That's not bad. It's not a perfect straight line, but it's pretty close. I did another example in the textbook on page 487. We have this discussion about cockpit noise in airplanes. And when they do the normal probability plot, they get this. There's a couple weird things at each end, aren't there? But most of it's a straight line. Yeah, that's pretty good. I did the exact same thing in Excel, because that is one of our recorded files, so I can just pull up the cockpit file. Share cockpit noise. Not this one, the other one. Here's our cockpit noise. And there's that normal probability plot. Mine looks different. Excel generates this differently than the statistical software they did. That's pretty staggered, but it's going up as we go across. I'm happy about that. I can actually look at the residuals themselves. Here are the actual residuals. across all of my data values. Those are the X values across the X axis here. The residuals are at the top and bottom, scattered across. Okay. If noise in the airplane, in the cockpit, was related to speed, I should expect the faster we go, the louder it gets. But I should also expect that the variation would be as much positive as it was negative. Whether I was at low speed or at high speed, I would expect the error to be plus or minus in either direction randomly, right? If this was lopsided and all of these were up or down, then I'd have an issue. But the fact that there are as many above as there are below, or at least roughly, and I don't see any sort of, hey, as we get faster, these get further apart, or as we get faster, these get closer together, this sort of spread as we go across in either direction, that idea would then violate that my errors were independent. These errors should be independent. There's a random chance of being up or down. There shouldn't be anything. Okay, if they made some sort of fan shape, whether that was going from left to right or right to left, some sort of expansion or contraction, the technical term for this is heteroscedasticity. I have never used that word outside of this one day in class. It literally means not uniformly scattered. Come on. Not uniformly scattered. Looks like a shotgun blast. That's exactly the effect I'm going for here. If that is the case, then there's some bias in my behavior. If I have some sort of fan out behavior, of some sort of fan in behavior. Top of page 488. I see these three pictures. And the middle and right pictures, those are the fan out and fan in behavior I'm looking at. Hey, these are much tighter to the x-axis. These are much further away as we go from left to right or the other way around. Heteroscedastic. I'm never using that word. But what this tells me is, oh, if there's no real pattern to that, then the chance of being a positive residual or a negative residual doesn't depend on how fast I'm going. The size of my residual doesn't depend on how fast I'm going. Therefore, this variance is constant across all of the behaviors. And that's an important idea. If I go back to the airplane one, is there any real line I could put on the bottom? Well, if I look at these two over here on the left, and I kind of draw a line down from there, well, I could see this side maybe going out. But that behavior is not reflected above because of these up here. So it's not the same on both sides. I either need the fan out to be the same on both sides or it doesn't cut. Again, these are things to tell me whether or not I should be able to use my least squares regression. I only can use that regression when I have all three of these variance properties covered. I need to have the same variance all the way across. I need to have that sort of normal distribution in my errors, and I need them to be independent of each other. Independence. Here's a question for you. If I move up, go from left to right, is there a clear pattern of switching between positive behavior and negative behavior in my residuals? Do these look like they tick back and forth, one up, one down, one up, one down? or 2 up, 2 down, 2 up, 2 down. I see back and forth, but I'm not sure I see it in a sequence. I can change that. I can ask Excel, hey, connect the dots. Are they moving back between positive and negative clearly? No. If there was some sort of pattern to the switching between positive and negative residuals, we'd call that an autocorrelated error. A simple autocorrelation is something in which we see this flipping back and forth in sign frequently. Bottom of page 489. Oh, there are a bunch of sign changes. There are a lot of sign changes. If the errors tend to be clustered, a lot positive, a lot negative, it's possible we'll have some sort of non-independence in the error. Somehow the error changes more closely related to where we are along the axis. Positive autocorrelation is more common in the data you are most likely to see. Why do I say that? You're a business statistician, ideally. You're doing this stuff for business purposes. Businesses have cycles, right? We have seasons where our sales are good and when they're lean. So we're going to see that sort of, oh, we had a growth here, then we had a contraction here. We're going to see that sort of cyclic behavior due to the nature of the business cycle itself.
Basically, all I was gonna say is that you're gonna have, like you said,
You're going to have cycles in every piece of business you do in some fashion. Ideally, we'll be able to account for that. But again, if I see that sort of autocorrelation, but the errors depend somehow on the previous errors, then I'm going to run into this problem. Now, I built the different pieces here. Let me go back and share this appropriately. This is our study hour example. There's our normal probability plot. Give me the next plot, please. There we go. This plot, I want you in the background. How do I push you to the back? Move to back. There it is. Send to back. Send to back. There. So here, I'm showing you the red one's the regression line. The blue ones are actuals. You can physically see each residual here. That's how far away we are with the red from the blue. And then our third plot, that's the wrong one. Where's my other plot? Here it is. My third plot, move you to the back now, is just the residuals again. This is where I'd be saying, oh, is there a fan out? Is there a fan in? Is there a frequent switch between positive and negative, or a less frequent switch between positive and negative? Well, I'm not sure I have enough data to really get a good fan pattern in this picture. The more data points I have, the more obvious that becomes. So I'm going to go ahead and say I don't think there's any sort of autocorrelation here, and I don't think there's any change in the variance as we look at the number of hours studied. If suddenly we had, everybody who studies a little, all of their residuals are small. Everybody who studies a lot, their residuals are big. Then I'd have some sort of a fan pattern. Questions? When I have large residuals, please notice there are a number of unusual observations here. These are the standardized residuals. If I look over at the left, that goes from -3 to 3 on the y-axis. Which means anything above above +2 or below -2, those are unusual. Nothing seems to be outside the ±3 range, so I don't think I have anything that's truly an outlier. But those things can cause a lot of shift in the regression equation itself. Let's consider our scatter plot. Where is my actual scatter plot? I promise I did a scatter plot somewhere. No, we'll do it again. Fine. Insert scatter plot. Boop. Now, again, I look at this and I'm disturbed because they started my y-axis at 80. That bothers me. So I'm going to change that. I go over here to the y-axis. I say format the axis, and I'm going to tell it to start at 0. There. It's a lot more clustered together that way, isn't it? I now see much more of a linear trend here. And when I put the trend line with its equation and R value, blow that up so I can read it. There. I notice that that's a pretty high R. What's the square root of that? R squared there is 0.895. What's the square root of 0.895? So my correlation coefficient is 0.946. What's that R squared called again? Coefficient of something. Correlation is just R. What's R squared?
Coefficient of determination.
Determination. And that tells me that 89.5% of the variation in noise is due to airspeed. So really, it's airspeed that's the huge determining factor. Only 10.5% of anything else matters to how much noise there is. Maybe it's the type of plane, the thickness of the fuselage. Well, this is cockpit noise. So it's the thickness of the glass. It's the type of insulation used. It's the thickness of the aluminum skin being used. 90% of the noise is just due to how fast we're going. Everything else is irrelevant. There is one X value all the way at this end. One X value all the way at this end. The lowest airspeed we have is 250. Sorry, 230. The highest airspeed we have, come on, give me the actual dot. No, won't give it to me. I need to sort those if I want to try and figure out which one's the lowest, which one's the highest. But they're still all fairly close together, aren't they? Here, on page 493, I have a scatter plot. Notice the two circle dots. There's nothing between here and here. That whole space is empty. Same thing, given the average of the X values, in this case representing hours worked, this one person is a workaholic, working almost 65 hours a week. This person is working 12 hours a week. I got a slacker, I got a workaholic. The average is somewhere in the middle here. If this person had their dot moved, what would happen to the line of regression? If I just moved it up or down? The line of regression should move with the dot. So this one person has a lot of influence over this regression line. In spite of all the other data, this one outlier is really going to push how far this line of regression goes up or down. There's a way to compute this. It's called leverage. Now, again, I will tell you with 100% certainty, I hate this calculation. Take the variance for that one person, the residual squared, and divide it by the variance. So I'm looking at the variance of that one person over the variance of the whole group. And if their variance is substantially higher, this is going to be a big number, right? Well, what the book says is if this sum is bigger than 4n, 4 over n, where n is the number of people, that's considered a high leverage. And this number is always positive because it's a bunch of squares being added, and n is a positive number. So this is never going to be negative. Whether that person is above the mean or below the mean isn't going to be important, but a high leverage ability, oh, yeah, they're at the end of the lever that is my regression line. If I move this one, the whole line moves. A lot of data analysis, a lot of statisticians, and a lot of people will tell you, if you've got somebody who's way far out that's a high leverage outlier, what you do with that piece of data? And that's where we did things like trimmed means, right? In case we had that one outlier, throw it away. It's also why we use things like medians instead of means in many situations. There are a lot of places where we have the ability to measure this. Excel does not calculate leverage automatically. Unfortunately for us, if I want to do leverage, I have to do it manually. I did, and it sucks. But in this particular example with all of the cockpit noise idea, there were 61 observations. Grab your calculator. What's 4 over 61? So multiply that by 4. No, that is 4 over. So I need to look at these leverages, which I calculated for each one of these numbers. See, here's this person. It's kind of hard to read. I took their value minus the average x, so their x minus the average x, and divided by our sum of squares, the residual squares. That's this number. I'm looking for those to be bigger than, what did you say, 0.6?
0.06.
So I start looking, oh, that one's really close. That's almost a high leverage. Oh, there they are. There are my two high leverage pieces. 0.6067, 0.09. Oh, okay, those are high leverage. That's observations 27 and 28. Can't really tell where they are here, can I? 27 and 28, based on my leverage, that's, oh, wait. The one with the highest leverage is the one with the lowest airspeed. It's the one all the way at the far end on the left. Just like in our example in the textbook, it's the one at the end of the lever. This one with 420.97 is not quite at the other end, but it is the one of the furthest away in the X-ray. So these are the two furthest out. They are my leverage. And if I go back and I look at that regression line, it goes exactly through both of those dots, doesn't it? So if I moved one of them, I could very well move the whole thing. StatLab, Minitab, Power BI, and a lot of other statistical software, SPSS, they have built-in algorithms to do leverage. This is actually a really easy piece of Python code. And I think it's part of the data analytics course to examine how to measure leverage. But for the most part, it's a matter of visual observation. I look at the data. This looks way far away from the center of the data. I should probably have trimmed it off. These are called influential observations most of the time. They have a lot of influence over the path of our regression. I don't want you doing residual calculations by hand ever. So if I ask you to do anything with residuals, I'm going to expect you to do an Excel and chop it out immediately. The StatLab software that came with the textbook, if you've got access to that, I didn't require it of you. You're welcome to use that too. It's got the ability to do leverage in it, but Excel doesn't. So my opinion on looking at developing leverage is to look at this line. Question? Non-normal distribution of error, non-constant variance, and correlation between the residuals leads me to believe that things in my least square regression will not predict accurately. So as much as I like using the method of least squares to make these predictions, it's possible that what I really want is something else. If I look at the trend line itself, and now I've pulled back up the trend line format, you'll notice there are other things I can use. I've checked the box that says linear. But what if I think this data really isn't linear? What if I think it's got some sort of periodic behavior to it based on a business cycle, based on season? I know for a fact, I'm pretty sure I sell less suntan lotion in December in Pittsburgh. Do you know they sell more suntan lotion, more sunscreen in December in Alaska? Why?
Because the sun reflects off the snow, making the UV rays actually really, really, really bad.
You get sunburnt from the snowpack. Things you never would have thought of. I'm going to go outside. It's 3 degrees below zero and I'm going to get frozen. And yeah, I'm going to go out and have a great time skiing and I'm going to get sunburned from the snow glaring up at me. Okay. I could change this. I have lots of options. Notice if I change the type of equation to be something else, I'll get a different picture potentially. The hell is that? Oh, that's a moving average, but it's averaging things in order over there. So the line is all screwed up because it keeps bouncing back and forth because those aren't in order. And I can increase the period of that so it takes more of them into account. But it would help if I sorted that. So let's go back, sort, custom, sort by airspeed, smallest to largest. Go. Now they're sorted in order, and you see how it isn't quite a straight line anymore? There's that flicker between them. I think I probably need to change the y-axis to make this look better. For me to be able to see it. You see how the step appears. We're only averaging 3 or 4 numbers at a time and tracking that as a trend. So it jumps in bursts. A moving average like that is actually a useful thing if you're measuring something that will change more over time. In this case, I'm looking at the airspeed, but I could just as easily look at a different data file. This data file is measuring gas mileage for my car per tank for the last 11 years. It's an old car. Pretty much. There's not a lot of high leverage pieces in here, are there? Not a huge set of residuals. I've got some pieces that might be unusual or outliers at the beginning here, but pretty much I got a good idea here. I cheat. Data-driven person, right? That's the cost of gas. Every time I put gas in the car. Since 11 years ago. What happened here? Actually, COVID is here. There's April of 19. So we got, I would love to agree with that. The war would be a good thing that would make gas prices rise. That's true. But that isn't actually what happened in this case.
They started letting people do stuff again.
We got out of COVID. So people started driving again. So gas prices went back up because we needed to build back up the amount of gas in the country, which means the imports went up and there was a lag in time and prices shot up. And they've been coming down since. But this is we got out of COVID. There's a correlation in what's going on. Would a straight line help me here? A straight line wouldn't give me anything useful in this case. Yes, gas prices have gone up, but there's been enough variation in what's going on over 11 years that I don't think I could draw a straight line trend and get useful information. I like having least squares and regression lines, but they aren't always going to give me useful data. What will give me the most useful data is asking the question, are these things related? There's nothing about cause, but are they related to one another? And if there is a relationship, can I gain any insight from that? It's the whole purpose of this type of regression analysis. Questions? Guess what? That's the end of chapter 12, which is the end of the material for this text. And that means on Monday, I will answer any question you have regarding the exam, regarding the text, regarding next semester, whatever you want to talk about. I did post some review questions for chapters 11 and 12. Take a look at those. If you have questions, I'd love to answer those on Monday. Your chapter 12 homework is due then. Unfortunately, that means we don't have anything except a weekend between then and now. So if you have questions about that, email me. All right? We'll see you all on Monday. Thank you very much for a lovely semester. Fill out your evaluation. Let me know how this term went, because I got to do it again next term and I might as well learn from you all.